In the world, there are chemical substances with such tremendous reactivity that almost nothing can withstand their destructive power. They're capable of corroding metals within seconds, igniting organic materials, or causing irreversible changes in substances they come into contact with. Even a negligible amount of such compounds can trigger chain reactions whose consequences are difficult to control. In this video, I invite you to explore the most dangerous and destructive chemical substances. Enjoy watching. I think everyone has heard of sodium. Today, you can find many videos in which this shiny metal is easily cut with an ordinary knife. This causes shock because we're used to the idea that doing this with most other metals at room temperature is impossible. The secret of this trick lies in the fact that sodium belongs to the alkali metals, elements of the first group of the periodic table of chemical elements. Other alkali metals, such as lithium, also share similar softness and lightness. Sodium was discovered in 1807 by the English chemist Humphrey Davy. He managed to isolate it using electric current. Since then, scientists have learned many interesting things about this metal. The main property of sodium is its incredible tendency to react with almost any substance. It reacts especially violently with water. Upon contact, the release of hydrogen and heat begins instantly. Sometimes the reaction is so strong that the hydrogen ignites, and if too much of it accumulates, an explosion may occur. That is why sodium can only be handled under special conditions and in strict compliance with safety rules. Despite its capricious nature, sodium has found applications in many fields. In nuclear power engineering, it is used as a coolant in reactors. In industry, it helps create various chemical substances. Interestingly, sodium is even used in street lamps. It produces a bright yellow light, and such lamps can operate for more than 12,000 hours. Because of its high reactivity, specific rules must be followed when storing sodium. As a rule, it is kept under a layer of kerosene or mineral oil in sealed containers away from water and easily flammable substances. Sodium is one of the most abundant elements on Earth, yet in its pure form, it does not occur in nature. This element is part of many minerals and is contained in ocean water. In living organisms, sodium ions help transmit nerve impulses. So despite its dangerous temperament, sodium is an important and useful element that serves humanity in many areas of life. The rare chemical element polonium was discovered in 1898 by Pierre Curie and Marie Sklodowska-Curie and was named in honor of Mary's homeland, Poland. This element is formed in extremely small quantities in the Earth's crust and is also produced artificially in nuclear reactors. Polonium-210 is an isotope of one of the rarest and most dangerous elements on Earth, polonium. It is formed as a result of the decay of uranium-238 and radium-226. Each atom of polonium-210 is unstable. It continuously emits alpha particles, rapidly losing mass and transforming into other elements. This process is known as radioactive decay and is accompanied by the release of enormous energy. It is worth noting that the half-life of polonium-210 is only 138 days. For comparison, uranium-238 decays over billions of years. This means that polonium-210 releases energy of incredible intensity. In addition to its power, this isotope is notorious for its danger and insidiousness to humans. The point is that its alpha particles cannot penetrate the skin from the outside, but become deadly if the substance enters the body with food, water, or inhaled dust. In that case, the radiation strikes directly at the cells, destroying their structure and DNA. A microscopic dose, less than a milligram, is sufficient to trigger an irreversible process of tissue destruction. Polonium-210 gained wide public attention in 2006 in connection with the death of Alexander Litvinenko, a former officer of the Russian security services who had received asylum in the United Kingdom. It all began with an ordinary meeting in a London cafe, where Litvinenko drank tea. Within a few hours, his condition deteriorated sharply. Doctors were unable to establish a diagnosis for a long time until tests revealed traces of a radioactive substance. The investigation determined that polonium-210 in liquid form had been added to the tea. Despite the dose being extremely small, it was sufficient to slowly kill Litvinenko. The death of the former officer became the first widely known case of the use of a radioactive element as a poison. In chemistry, there is an extraordinary solution with an unusual name and incredible power. It is Aqua regia, or royal water. Although the name may suggest an alcoholic drink, in reality it is a destructive mixture of two acids, hydrochloric and nitric, mixed in a proportion of 1:3 by volume. A freshly prepared mixture is almost colorless, but very quickly it turns yellow-orange and begins to fume, releasing a sharp, unpleasant odor. But why was this solution called royal? The reason is that Aqua regia is capable of dissolving gold, which has long been called the king of metals because of its remarkable resistance. Gold does not rust, does not tarnish over time, and does not yield to the action of most acids. Yet, royal water literally makes gold disappear, turning it into a solution. In a similar way, the mixture can also dissolve platinum and palladium. The secret of the solution's action lies in the coordinated work of the two acids. Nitric acid acts as an oxidizing agent. It attacks the metal, releasing active oxygen. Hydrochloric acid, in turn, supplies chloride ions, which bind to metal ions and form soluble complex compounds. As a result, gold seems to melt in the liquid, transforming into chloroauric acid. The history of Aqua regia goes back deep into the past. The first references to a similar mixture can be found in Arabic alchemical treatises of the 8th century. During the Second World War, it was even used to save the gold medals of Nobel Prize laureates, German physicists Max von Laue and James Franck. In 1941, the Hungarian chemist György de Hevesi dissolved the metals in the solution to prevent their confiscation. The mixture containing the dissolved gold was stored in the laboratory of the Niels Bohr Institute as an ordinary chemical bottle. After the war, the gold was extracted from the solution, and the Swedish Royal Academy of Sciences cast new metals which were returned to the laureates. Aqua regia is actively used to extract precious metals from old electronic equipment, as well as to clean glassware from organic and metallic contaminants. However, despite its usefulness, it is an extremely difficult solution to handle. Royal water cannot be stored. It is prepared immediately before use because over time it decomposes and loses its strength. In addition, the solution is highly aggressive and dangerous. It releases toxic gases, causes severe chemical burns, and can even lead to an explosion if handled improperly. Therefore, only specialists wearing protective clothing, goggles, and gloves, and working under a fume hood are allowed to work with Aqua regia. Experimenting with this liquid at home is strictly prohibited. Oleum is an unusual and rather dangerous chemical substance, also known as fuming sulfuric acid. Oleum is a solution of sulfur trioxide in concentrated sulfuric acid. It usually appears as an oily liquid that fumes in air. This happens because its vapors react with moisture, forming tiny droplets of sulfuric acid. The distinctive feature of oleum is its extremely high reactivity. It is not just a strong acid, but a true chemical anomaly. capable of reactions that ordinary sulfuric acid cannot perform. Above all, oleum has the ability to remove water even from substances that seem completely non-aqueous. Because of this property, oleum chars organic materials by drawing water out of them. For example, if a drop is placed on sugar, it turns into a black, porous mass of carbon. This occurs because when oleum comes into contact with water inside a substance, even if only a very small amount is present, a violent exothermic reaction takes place. Boiling occurs, releasing enormous amounts of heat and forming even more sulfuric acid. Oleum easily corrodes most known materials, from wood and fabric to metals. In addition, it is extremely dangerous to humans and can cause very severe burns to the skin and mucous membranes. However, oleum has found wide application in various fields of human activity. In industry, it serves as an intermediate product for the production of concentrated sulfuric acid. In organic chemistry, it is used as a powerful dehydrating and oxidizing reagent, for example, in the synthesis of certain explosives. Oleum is also actively used to obtain anhydrous acidic mixtures where the presence of water is unacceptable. Working with oleum is possible only under special conditions, in protective equipment, in rooms with powerful ventilation, and with strict adherence to safety rules. Despite its danger, this substance is indispensable where the maximum chemical strength of sulfuric acid in a concentrated form is required. Hydrofluoric acid, also known as fluoric acid, is an aqueous solution of hydrogen fluoride gas, abbreviated as HF. In appearance, it looks like ordinary clear water and has almost no smell. However, behind this external simplicity lies great danger and highly unusual properties. The history of hydrofluoric acid began in 1771 when the Swedish chemist Carl Wilhelm Scheele first obtained this compound. For a long time, working with the acid was almost impossible because it mercilessly corroded glass laboratory equipment. Only with the advent of platinum vessels did scientists learn how to handle it and apply its effectiveness. Hydrofluoric acid is known for its unusual properties. Unlike familiar acids, such as hydrochloric or sulfuric acid, hydrofluoric acid does not readily dissociate in water into active ions. Its molecules remain intact, and because of this, they can easily penetrate deep into materials and living tissues. The most striking property of hydrofluoric acid is its ability to dissolve glass. Hydrofluoric acid has found wide application in many areas of industry. In microelectronics, it is used to clean silicon wafers for microchips. In oil extraction, it helps dissolve rock formations in wells. In addition, it is used to decompose many minerals to create matte patterns on glass, and as a raw material for the production of fluoroplastics and refrigerants. Despite all its advantages, hydrofluoric acid is extremely dangerous and insidious. When it comes into contact with the skin, it does not cause immediate pain, but after several hours, a severe burn develops at the site of contact. Acid vapors irritate the respiratory tract and can lead to pulmonary edema. If it enters the body, it disrupts organ function and the balance of salts. When working with hydrofluoric acid, strict safety measures must be observed, and one should never forget that behind its transparency lies a force that demands extreme caution. Bromine is known as a chemical element that under normal conditions is a heavy liquid of reddish-brown color. It has a sharp, unpleasant odor, somewhat reminiscent of chlorine and iodine. Unlike most other nonmetals, bromine remains liquid at room temperature. Chemically, bromine is very reactive and readily enters into reactions with other substances. For example, it actively reacts with metals, forming salts called bromides. Bromine also reacts with organic substances. Its atoms can replace hydrogen in molecules, changing their properties. However, bromine does not react with silver, lead, or platinum. In nature, bromine does not occur in a pure form because of its high reactivity. Its compounds, bromides, are found in seawater, salt lakes, underground brines, and certain rocks. The main sources for bromine production are natural brines, seawater, or byproducts of potash production. Bromine is capable of destroying many materials. It causes corrosion of metals, especially in conditions of high humidity. Organic materials, fabrics, rubber, and some plastics gradually lose strength and degrade when in contact with bromine. For humans, bromine and its vapors are very dangerous. Inhalation of bromine vapors, even at low concentrations, immediately causes irritation of the nose and throat, coughing, dizziness, and nosebleeds. With stronger exposure, spasms of the respiratory tract and suffocation may occur. If liquid bromine comes into contact with the skin, it causes severe burns, and contact with the eyes can lead to loss of vision. It may seem surprising why such a dangerous substance is needed. However, despite its hazards, bromine is also very useful. It is applied in many fields. Bromine is used in the production of flame retardants, additives that make plastics, wood, and fabrics more fire-resistant. In photography, silver bromide serves as a light-sensitive material. In oil extraction, bromide solutions help increase well productivity. In addition, bromine is necessary for the production of certain medicines, as well as pesticides and insecticides. Sometimes bromine, more precisely bromine pentafluoride, is used as a component of rocket fuel since it is a very strong oxidizer. Thanks to its chemical properties, bromine finds application in many industries, but it requires extremely careful handling and strict adherence to safety regulations. Thionyl chloride is a clear, mobile liquid with a sharp, choking odor. By its nature, thionyl chloride is a highly active reagent that readily donates chlorine atoms and binds water. This very ability determines its value in chemistry. For example, if thionyl chloride is added to an alcohol, an alkyl chloride is formed, and the reaction proceeds very quickly. In the same way, it converts carboxylic acids into acid chlorides, key intermediates in the synthesis of medicines, plastics, and other complex compounds. It is precisely the reaction speed and the high yield of the final product without contamination that make thionyl chloride an indispensable assistant for chemists. In addition, it reacts violently with almost anything that contains water. Upon contact, intense hissing begins and corrosive gases are released. It actively interacts with metals, alkalis, and many organic compounds. When heated, it can decompose with the release of chlorine, and with certain substances, it can form explosive mixtures. In industry, thionyl chloride is indispensable in the production of pharmaceutical substances, agrochemicals, dyes, and polymer materials. In laboratories, it is valued as a reliable reagent for obtaining acid chlorides and modifying organic molecules. However, despite its usefulness, due to the high reactivity of thionyl chloride, working with it requires strict safety measures. A fume hood, protective goggles, gloves, and a lab coat are mandatory. The reagent must be stored in sealed containers, away from moisture and oxidizing agents. Even a small amount of spilled thionyl chloride causes severe irritation of the eyes and respiratory tract, and inhalation of its vapors is dangerous to health. Imagine a liquid that can deal with almost any organic material, like a school of predatory fish. Such a mixture exists, and it is called the Piranha solution. The Piranha solution is one of the most aggressive cleaning mixtures in chemistry. It is prepared immediately before use by mixing concentrated sulfuric acid and a hydrogen peroxide in a proportion of 3:1 or 4:1. Sometimes, a small amount of ammonia is added to this solution, producing what is known as alkaline piranha. let us take a closer look at how this chemical predator works. When the substances are mixed, a violent reaction occurs with the release of highly active oxygen species. These particles literally tear apart organic molecules. As a result, complex compounds are converted into water and carbon dioxide as if dissolving without a trace. Because of such aggressiveness and merciless action, the solution received its name after the piranha fish. Because the mixture is extremely dangerous, it is handled only in laboratories and industrial settings. The solution has proven itself as an effective means for cleaning glass and quartzware from the most stubborn organic contaminants. In addition, it is used in the manufacture of semiconductors and microchips, as well as for treating oxidized glass filters where conventional cleaning methods cannot reach. When working with a piranha solution, specialists never forget how dangerous it is. The mixture heats up strongly during preparation and may boil and splash out. It corrodes skin and fabrics, causing severe burns. In addition, the solution releases oxygen, which means that when it comes into contact with flammable materials, a fire or explosion may occur. The solution cannot be stored, since over time it becomes even more dangerous. Despite its incredible aggressiveness, some materials are still able to withstand an encounter with piranha. These include quartz and special heat-resistant glass, but only for a short time. Certain types of ceramics, items made of platinum and gold, as well as Teflon. Sodium hydroxide is a chemical substance also known as caustic soda or lye. It appears as white crystals or granules, very similar to coarse salt, but with completely different properties. It is one of the strongest alkalis, and it must be handled with extreme caution. People have been familiar with this substance for a very long time. Even in ancient times, natural alkalis were used for washing and treating fabrics. However, a clear understanding that this substance was specifically sodium hydroxide appeared only in the 18th century, after the French scientist Henri-Louis Duhamel du Monceau first distinguished different types of alkalis and gave them separate names in the year 1736. Industrial production began much later, in the 19th century, when methods were developed to produce this substance in large quantities. The main property of sodium hydroxide is its strong affinity for water. If left in the open air, it begins to absorb moisture and gradually spreads. When dissolved in water, an interesting process occurs. The water heats up strongly. This happens because a large amount of heat is released during dissolution. Thanks to this property, sodium hydroxide has found wide application and remains in high demand in the modern world. In soap making, it helps convert fats into soap, a process known as saponification. Without sodium hydroxide, it would be impossible to produce ordinary soap, laundry detergent, or shampoo. In paper mills, it is used to produce paper. Wood is boiled in alkali and turns into cellulose, the basis of paper. Thanks to this process, we obtain white and durable paper for books, notebooks, and packaging. In the textile industry, sodium hydroxide improves fabrics. When cotton is treated with alkali, it becomes stronger, more attractive, and easier to dye. Chemists use sodium hydroxide to produce a wide range of substances, from plastics and synthetic fibers to medicines and dyes. In oil refining, it helps purify fuel from harmful impurities. Sodium hydroxide is also used in plumbing to remove blockages in sewer pipes. It is even sometimes found in food products as the food additive E524. However, this substance also has dangerous aspects. Sodium hydroxide is extremely caustic. It can corrode skin, cause severe burns, and even lead to loss of vision if it comes into contact with the eyes. Therefore, it can only be handled with proper protective equipment. Osmium tetroxide is a chemical compound of osmium with oxygen, appearing as dark brown or black crystals. Osmium is one of the heaviest and rarest metals and its compounds often exhibit pronounced oxidizing properties. Osmium tetroxide is distinguished by exceptionally high chemical activity. It is a powerful oxidizing agent that readily reacts with most organic substances. Such reactions are often accompanied by explosions or ignition. Even at room temperature, the compound is capable of oxidizing many materials that do not react with other oxidizers. When heated, its activity increases sharply. Osmium tetroxide can ignite paper, wood, and rubber. In aqueous solutions, it forms osmic acid, which also shows strong oxidizing properties. Because of such aggressiveness, the use of osmium tetroxide is strictly limited and requires special conditions. It is mainly used in scientific research. In organic chemistry, the compound acts as a catalyst or reagent for the oxidation of complex compounds, as well as for the synthesis of other osmium compounds. In microscopy, it serves as a contrast agent. Its solutions stain biological samples, making fine cellular structures visible in electron microscopy. In some cases, the compound is used in analytical chemistry to detect certain substances. I think there is no doubt that osmium tetroxide possesses tremendous power, but it is precisely this power that makes it extremely dangerous. This compound is highly toxic. Even small amounts of vapors or dust can cause severe damage to the respiratory tract, eyes, and skin. In addition, all heavy metals, including osmium, are capable of accumulating in the body and causing chronic poisoning. Chlorine trifluoride is a chemical substance composed of chlorine and fluorine atoms. At room temperature, it is a colorless gas with a sharp and unpleasant odor, and when cooled, it turns into a pale green liquid which becomes completely transparent upon further cooling. This compound is known for its incredible aggressiveness. Chlorine trifluoride is capable of reacting with almost anything, and in many cases, these reactions proceed violently, releasing large amounts of heat and sometimes ending in an explosion. This substance is truly dangerous. It can ignite even materials that we usually consider non-flammable, such as glass or asbestos. Chlorine trifluoride readily reacts with metals, even if they are covered with a protective oxide film, and it destroys organic substances while releasing toxic gases. Chlorine trifluoride also poses a serious threat to human health. Its vapors are highly toxic. If inhaled, they can cause severe damage to the respiratory tract. Even a very small amount of this gas in the air can be dangerous. Chlorine trifluoride corrodes almost all materials, from metals to ceramics and concrete. There is a known case when a leak occurred at a chemical plant. A small amount of the cool liquid substance spilled onto the concrete floor of a workshop. Almost instantly, a violent interaction began with the components of the concrete, silicates, aluminates, and the water contained within it. The reaction was accompanied by the release of heat and various gases, including toxic silicon tetrafluoride and chlorine. The concrete began to bubble, crack, and crumble. In just a few minutes, a crater formed in the floor with a depth of about 30 centimeters and a diameter of approximately 1 meter. The released gases not only destroyed the concrete, but also caused corrosion of metal structures, and the poisonous vapors created a serious threat to people. The incident clearly demonstrated how dangerous chlorine trifluoride is and how important it is to observe strict safety measures when working with it. However, despite all the dangers, this compound finds application in some high-technology fields. For example, in the nuclear industry, it is used to clean equipment from uranium and plutonium oxides. In microelectronics manufacturing, chlorine trifluoride helps process silicon wafers and remove metal residues. It is also used to obtain especially pure fluorides of rare metals and in experimental types of rocket fuel. Fluorine azide is one of the most unstable compounds in chemistry. In terms of composition, it appears extremely simple. just one fluorine atom and 3 nitrogen atoms assembled into an azide group. But behind this modest formula lies a colossal reserve of energy, ready to be released at any suitable moment. In appearance, fluorine azide is a pale yellow gas. At first glance, it may seem harmless, but chemists know how destructive its power is. The secret of the extraordinary reactivity of fluorine azide lies in the very structure of its molecule. The azide group stores an enormous amount of energy, and the bond between fluorine and the azide is so fragile that any external influence can break it. Once this happens, the accumulated energy is released in fractions of a second, turning into a powerful explosion. Even a light touch, slight heating, or barely perceptible vibration can trigger this process. The power of fluorine azide is astonishing. Its explosive force exceeds that of many traditional explosives. Sometimes, even a single microgram of this compound is enough to cause a sharp, deafening explosion with a bright flash of light. Moreover, during the explosion of fluorine azide, toxic decomposition products are formed, fluorides and nitrogen oxides, which themselves pose a serious danger. Despite its impressive power, practical application of fluorine azide is virtually impossible. Its extreme instability rules out its use in industry or military technology. The only place where it is handled is in specialized scientific laboratories. There, fluorine azide serves as a valuable object of research. Scientists study it as a model high-energy compound, seek to understand the mechanisms of ultra-fast chemical reactions, and investigate the properties of unstable molecules. Potassium is a chemical element of the first group of the periodic table developed by Dmitry Ivanovich Mendeleev. This alkali metal in its pure form has a soft structure and a silvery color. In nature, it is almost never found in its pure state because it immediately reacts with other substances. It is precisely for its reactivity that this chemical element is known. Potassium behaves most dangerously when it comes into contact with water. Their interaction results in a violent reaction. The metal first begins to hiss, then melts, and then, as a rule, ignites or even explodes. As a result of this interaction, a caustic alkali and a flammable gas are formed. In air, potassium is also unstable. It oxidizes quickly and can spontaneously ignite. Another feature of potassium is its destructive power. It is capable of corroding metal containers if stored improperly, as well as damaging wood, fabric, and paper when in contact with the molten substance. Potassium is, of course, dangerous to humans as well. In its highly reactive state, it can cause severe burns if it comes into contact with the skin or eyes. Despite its explosive nature, potassium is actively used in various fields of human activity. For example, in nuclear reactors, an alloy of potassium and sodium serves as a coolant, and in the chemical industry, it acts as a catalyst or a reducing agent. Dimethyl mercury is an organic compound in which a mercury atom is bonded to 2 methyl radicals of the CH3 group. At room temperature, this substance is a colorless, easily evaporating liquid with a faint, sweetish odor. Externally, dimethyl mercury appears harmless, but in reality it belongs to the most toxic chemical compounds known to humanity. The distinctive feature of dimethyl mercury lies in its exceptional ability to penetrate biological barriers. Unlike inorganic mercury compounds, it easily passes through the skin, mucous membranes, and even through some protective materials. Inside the body, the substance rapidly breaks down, releasing mercury ions that irreversibly damage the nervous system, kidneys, and other organs. In terms of toxicity, dimethyl mercury surpasses ordinary mercury and its inorganic salts many times over. A lethal dose for humans may amount to only a few milliliters. and the symptoms of poisoning often appear weeks or months after contact, which makes diagnosis extremely difficult. Even microscopic amounts that come into contact with the skin can cause fatal poisoning. Dimethyl mercury has virtually no practical applications. In the past, it was used in scientific research as a reference toxicant or to study the mechanisms of mercury poisoning. Occasionally, the compound was used in analytical chemistry to calibrate instruments that determine mercury content. Today, its synthesis and use are strictly limited due to its extreme danger. Fluoroantimonic acid is one of the strongest and most dangerous acids in the world. This substance belongs to the class of superacids, which are capable of penetrating even those compounds that are usually considered chemically inert. In terms of strength, fluoroantimonic acid surpasses ordinary sulfuric acid by millions of times, and here is why. A typical acid, such as sulfuric acid, simply donates its proton, a positively charged particle, to another substance. Fluoroantimonic acid acts differently. It not only gives up a proton with great ease, but also creates a very stable negative ion. Thanks to this, it literally attaches protons to a wide variety of substances, even to those that normally do not react with acids at all. For example, consider Teflon, the material used to make non-stick coatings. It is famous for reacting with almost nothing, yet even it is not completely protected from fluoroantimonic acid. If they are left together for a long time, the acid will gradually begin to destroy Teflon. However, during short contact, Teflon can still withstand the effect, which is why it is sometimes used to temporarily store this dangerous liquid. Working with fluoroantimonic acid is extremely difficult and hazardous. When it comes into contact with skin, it causes severe burns, and inhalation of its vapors can seriously damage the respiratory tract. If fluoroantimonic acid is combined with water, a violent reaction begins with the release of heat and toxic gases, and an explosion may occur. Fluoroantimonic acid is used in the chemical industry and in scientific laboratories. It is employed to initiate reactions with substances that normally refuse to interact. The acid is also effective in the development of new types of fuel, in studying the behavior of protons when they attach to different molecules, and in creating superacidic environments for experiments. White phosphorus is a special form of ordinary phosphorus. In appearance, it resembles wax or paraffin. It can be cut with a knife or even kneaded with fingers. White phosphorus truly looks harmless, but in reality it is a very reactive and dangerous substance. The most famous property of white phosphorus is its violent reaction with oxygen. During oxidation, various chemical compounds are formed, including phosphorus anhydride, which later turns into phosphoric acid by absorbing moisture from the air. However, the main danger of white phosphorus lies in the fact that it can easily ignite on its own. A temperature of about 33 to 34 degrees Celsius is enough for it to ignite upon contact with air. If the phosphorus is crushed or spread in a thin layer, it can ignite at an even lower temperature. When it burns, a huge amount of heat is released. The temperature can reach 1200 degrees Celsius and thick white smoke forms around it. Because of such fire hazard, white phosphorus must be stored with extreme care. Most often it is kept underwater since this prevents contact with air and eliminates the risk of ignition. Sometimes, white phosphorus is placed in special sealed containers or stored in an atmosphere of inert gas, which prevents it from reacting with oxygen. Another dangerous feature of white phosphorus is its toxicity. White phosphorus is extremely toxic. Its vapors and combustion products irritate the eyes, nose, throat, and lungs, causing severe discomfort. When even a small amount comes into contact with the skin, it leads to long-lasting burns, because the phosphorus literally melts into the tissues and continues to burn. Despite all these dangers, white phosphorus finds use in various fields. In the past, it was used in the production of matches, but after it was discovered that it caused necrosis of the lower jaw, this use was abandoned. Today, white phosphorus is used to produce phosphoric acid and various phosphorus compounds, which are then applied in industry. In agriculture, fertilizers based on it help plants grow. In metallurgy, phosphorus is used to improve the properties of certain alloys. It can be concluded that white phosphorus is a substance with a dual nature. On the one hand, it is useful for science and industry. On the other, it poses a serious threat if handled carelessly. That is why scientists and engineers constantly seek ways to use its beneficial properties while minimizing risks to people and the environment. Nitric acid is known to many as a very serious and dangerous acid that is often used in industry and laboratories. In concentrated form, it exists in two types, white fuming and red fuming. But what is the difference between them? White fuming nitric acid is an almost pure solution, without unnecessary impurities. It contains more than 90% of the acid itself and appears almost transparent. Although it is called fuming, the vapor above it is barely visible. Red fuming nitric acid differs in that a large amount of brown gas, nitrogen dioxide, is dissolved in it. This gas gives the acid its red-brown color and creates thick reddish fumes when the acid is left open. Both of these acids are extremely reactive. They are capable of corroding almost everything they come into contact with. Even a single drop can begin to destroy metal, wood, and even concrete. It is especially dangerous that when the acid reacts with the material, heat is very often released, meaning the material may not only dissolve, but can even ignite. Both red and white fuming nitric acid are dangerous to humans. If the acid comes into contact with the skin, it causes a severe burn, similar to fire, but even worse, because the reaction continues until the acid is washed away. In addition, acid vapors and brown gas irritate the eyes and respiratory tract. At high vapor concentrations, the lungs can be seriously damaged. So where are such dangerous substances used? It turns out they're very important in many fields. For example, in rocket engineering, red fumic nitric acid is used as a fuel component, helping the propellant burn more efficiently. In the chemical industry, it is used to produce many important substances, from fertilizers to dyes and explosives. In factories, the acid is used to clean metal parts before coating or to extract valuable metals from old scrap. In laboratories, it is used to dissolve solid samples for analysis. Working with such acids is possible only under strict regulations. Storage containers are made of special materials, glass, specialized plastics, or stainless steel, that the acid does not corrode. All pipelines and connections must be airtight so that not a single drop can leak out. Facilities are equipped with powerful ventilation systems to capture toxic vapors, and workers wear protective suits, gloves, goggles, and masks to prevent the acid from entering the body or lungs. In case of a leak, it is immediately neutralized with special solutions such as soda or alkali, and then everything is thoroughly rinsed with water. Working with these acids is allowed only in specialized facilities and laboratories. Using them at home for experiments is strictly prohibited. Fluorine is a well-known chemical element. It is the most reactive of all nonmetals. Under normal conditions, fluorine is a diatomic gas of pale yellow color with a sharp odor, and at cryogenic temperatures it turns into a yellow liquid or pale yellow crystals. In nature, fluorine occurs only in compounds. It practically does not exist freely on its own because it reacts instantly. As mentioned above, fluorine possesses extraordinary chemical activity, and in addition, it is known as the strongest oxidizing agent among all known elements. Fluorine is capable of taking electrons from most other substances, including those we usually consider inert. For example, fluorine reacts with some noble gases, and with hydrogen it explodes, even in the dark at room temperature. The power of fluorine is so great that it can ignite sand, react with metals even when they are covered with an oxide film, and interact with most organic substances, sometimes explosively. When fluorine comes into contact with water, it decomposes it with the release of oxygen and the formation of hydrogen fluoride. Hydrogen fluoride is a colorless gas with a sharp odor that dissolves easily in water, forming hydrofluoric acid. Hydrogen fluoride is released when fluorine reacts with hydrogen-containing substances, as well as during the decomposition of many fluorides. Hydrogen fluoride is extremely dangerous to humans. It severely corrodes tissues and can penetrate the body, where it begins to bind calcium ion, disrupting the function of the heart and nervous system. Even small amounts can cause severe poisoning, and at high concentrations, it can be fatal. Despite the danger, fluorine and its compounds are widely used in the production of Teflon and other polymers, in metallurgy, in the nuclear industry, and even in dentistry. Perchloric acid is the substance that literally burns everything in its path, releasing oxygen with such force that even metals begin to burn. If a drop of the acid is placed on paper or wood, the material ignites without any external flame because the acid itself initiates the combustion process. Even such resistant substances as sulfur or phosphorus ignite with a bright flame in its presence. The remarkable properties of perchloric acid are determined by its structure. In the molecule, 4 oxygen atoms surround a chlorine atom, creating a powerful reserve of oxidizing energy. When the acid enters into a reaction, it generously releases this oxygen, forcing other substances to oxidize at an unprecedented speed. It is like pouring fuel onto a fire. The reaction becomes rapid and uncontrollable. Its power is also evident in its interaction with metals. Gold and platinum, which are resistant to both hydrochloric and sulfuric acids, cannot withstand perchloric acid, although they do react with it more slowly. Perchloric acid is actively used in laboratories to decompose complex samples. In industry, it is applied in the production of explosives, and in microelectronics, it is used to etch the finest patterns on semiconductors. And that brings me to the end. If you enjoyed this video, don't forget to rate it, subscribe to the channel, and click the notification bell. Your activity is the best reward for me. Thank you for your attention. See you soon. Bye.